Perfect.
Okay.
Thank you so much, Bonnie.
You bet. Hope to see you on the site. We'll post jobs and scholarships as well as they come into us, so it's not a bad idea to just sign in. It'll just be that weekly campus announcement, Tuesday morning, 9 o'clock.
Great.
So, thank you.
Thank you. Okay. So write down this information if you want it. I know that I've sent this out to you a couple of times in those announcements. If you're not reading those announcements, start doing it. Do you guys know what we have coming up this week? At the end of the week? You have your unit test. And do you know what you need to do before your unit test? Could you just pass those back, please? Pass those behind you. No, this one is just- Pass that. You have a practice test. Is that optional? It is not optional. You have to take the practice test. It's actually part of your grade. It's part of your participation grades, but it's still a part of your grade. I think that's not enough. You want to pass them out? Thank you. Anybody not get one? So, you need to take your practice test sometime this week. I recommend doing it after we learn everything. How many attempts do you get at that practice test? 2 attempts. Use it. Do you need your lockdown browser on the practice test? You do not. You need your lockdown browser on the actual unit test. Where do you need to be for the actual unit test? Anywhere. But where do I recommend you being? Somewhere with good Wi-Fi. Don't let your Wi-Fi cut out during your 2-hour practice test. During your 2-hour unit test, because that would be a shame to lose all of that. We have that coming up this weekend, but as Bonnie mentioned, tomorrow is the drop deadline. I actually just had a student drop from the class because they were offered a full-time job and no longer really needed to take this class this semester. So things like that happen all the time, but you guys are now getting right up to that break point. So I hope that you guys are buckled in and that you're ready. I spent some time this weekend fixing that dang calendar. It almost made me cry. I apologize. I know how many emails I got from some of you saying, I'm so confused, I'm so lost. Other people saying, thank you for those announcement checklists because that's the only way I can navigate. Now the calendar should match closer to what I'm sending in those. But it is just so many assignments, and I can't really do anything about it because just changing them took me more than half an hour for my 3 sections. So I actually had to go all the way down to November towards like Thanksgiving break to adjust due dates. And that's because of this like week delay that we had early on in the semester. It was a pain. I hope it pays off though. So let me know if things still feel confusing as we go on. All right, did we finish up Module 2 on measurements? You guys feel good? Because there were a couple of things I never got to say, and we've got a lot to finish up in this week, Module 3 and Module 4, which is all of Unit 2. So the things that I want to say quickly. One of them wraps up significant figures and their rules. And I know a lot of you wrote about sig figs in your Feynman notes for Unit 1, which is great. We talked about rules with multiplication and division, correct? And rules with addition and subtraction. If it's addition or subtraction, you go to the least number of decimal places. If it's multiplication or division, you go to the least number of sig figs. Even if that increases the number of decimal places you have. Those of you that had me in lab last week know that sometimes you have 3 sig figs, 1 before the decimal, 2 after, and then you do some division, and you need 3 sig figs, and they're all after the decimal place. So these rules are mutually exclusive. Does that make sense? And then there's one last rule, which is rounding. And I think most of us know how to round. If the number is less than 5, you round down. If the number is greater than 5, you round up. Again, it's the number after your last significant figure that you're looking at. You don't look at anything past that. Except in the case of 5. Here we're using Banker's rounding. And I'll be honest, I had never heard of this until I taught this class. But it's what we're using. And it's not very hard. If you have a number that has 3 sig figs, okay, this number has how many sig figs as written? 4 sig figs. We're only allowed to have 3. That means that 5 needs to go. But notice that nothing comes after the 5. 5 actually hits the straddle point. So you can't say that 5 is closer to rounding up or rounding down. So Banker's rounding says, I hate it, but it's what it says. Round to the nearest even number. So 1 rounds to 2. Does that make sense? It's the same thing if we have a 5 followed by an infinite number of zeros. All of those zeros keep 5 exactly at 5. We still round to the nearest even number. But what happens if there is some non-zero after that 5 at some point? Well, it's not just 5. Now it is a number greater than 5. Earlier I said you never pay attention to any of the other numbers, just the one past your last significant figure. So this is the number we're trying to round. This is the number we're trying to round. This is the number we're trying to round. It's that next number that we're paying attention to. If it's a 1, a 2, a 3, a 4, followed by any numbers, you only pay attention to that 1, that 2, that 3, that 4. But if it's a 5, you can pay attention. If there are non-zeros after it, now it rounds up. It's a silly rule. It's not one that I was used to. Maybe this was a bad example, yeah, because they all went to the same, they all went to the same number. It's not one that I was used to, but it is what we're leaning with this semester. All right, so here's a mass. Can you round this to 3 significant figures? Yes, you can, Daniela. How do you round this to 3 significant figures? Does it become 500 or does it become 501? Correct. It's my last significant figure is followed by a 5, which means I've got 3 situations. 5 and nothing, 5 with only zeros, or 5 with something. And this is 5 with something. My other 2 situations would have kept it at 500. But because it's 5 and something, I round this to 501. 3 sig figs. Now at the end of class last week, I gave this multiplication example that really rocked you guys. I actually don't remember the numbers. Does anybody remember the numbers? It was dividing by 2, I know that, and I only had 1 unit. Somebody's got it, I know this. No? Meters, right?
Yeah.
divided by 2.0. Yeah, and I didn't have any units. And one question that came up was, isn't that a whole number, a counted number? Don't those have infinite significant figures? So I should still be limited to 3 in this measurement. And I said, yeah, but pretend it's a measurement. Okay, I can fix that. Here's the measurement. It's a unit S, which is seconds. Good. And notice that this is per seconds, right? Meters divided by seconds, which means we're actually talking about a frequency. Okay, so 2.52 divided by 2 seconds. That means I had a stopwatch. I didn't count the seconds. I measured the seconds. And I'm limited by my stopwatch to just 1 decimal place or 2 significant figures, because that's a trailing 0 that comes after a non-zero in a number with a decimal place. How many sig figs am I limited to? 2, because I'm doing multiplication or division. And the answer that I get is 1.26 meters per second. No. How many sig figs in 1.26? How many sig figs am I limited to? 2. So what do I round my number to? Well, first of all, identify the number you're going to round. What is the last significant figure? It's this 2. Is that digit certain or uncertain? Wrong. Your last significant figure is always your uncertain figure. How do you know? Because you're about to round it. Are you certain about that number? No way. You're rounding it because you know it's your last significant figure, but you're not certain about it. Yeah? So 1.26 meters per second rounds to become? Good. 1.3 meters per second. I fixed it. I thought long and hard about that example this weekend. Okay. Thanks, guys. The last thing I wanted to talk about was actually back in dimensional analysis and unit conversion. There's an example of unit conversion that can be really tricky, and I want to make sure that you guys have modeled it. Let's say that I am trying to figure out the mass of an ice cube. I know its density, and I have its volume. So its volume is 0.00157 cubic meters. That's V. Its density is 0.987. Actually, in lab, I think it's 9187 grams per cubic centimeter. I want to know its mass. So I'm trying to get something out of this. I'm changing the dimensions that I'm analyzing. I know its volume, but I want to understand its mass. That is the same thing I'm analyzing, just changing the dimension I'm analyzing it with. Yeah? So I need to do unit conversion. Obviously, I need to go from volume to mass using my unit conversion factor, density, which has 2 units, volume and mass. But notice that the units for my density do not match the units for my actual volume. So I need to first convert my volume into the same units as my conversion factor. So 0.00157 cubic meters. How many significant figures here? All of those zeros are leading, which means they are never significant. Leading zeros, never significant. trailing zeros in a number with a decimal are significant, and there are how many trailing zeros? None. So 3 significant figures, only the non-zeros. I need to convert out of cubic meters. Where do I put it? On the bottom, cubic meters. I need to convert into what? Not just centimeters, cubic centimeters. How many times does a cubic centimeter go into a cubic meter? Your brain should think 1 to 100, right? Centimeters to meters. Here's how I want you to rewrite these units. This is not cubic meters. This is meter times meter times meter. And this is not cubic centimeters. This is centimeters times centimeters times centimeters. I'm not converting cubic meters. I'm converting meters and meters and meters. I'm converting it 3 times. So how many times does centimeters go into meters? Times how many times does centimeters go into meters? Times how many times does centimeters go into meters? That's what we're looking for. Okay, now I hope intuitively you know that the conversion is 1 to 100. But which one gets 1? Which one gets 100? First, what's the bigger number, 1 or 100? 100. What's the smaller unit? So 100 centimeters to 1 meter. That's what we're going to plug in here. 1 meter, 100 centimeters. 1 meter, 100 centimeters. 1 meter, 100 centimeters. Second.
On the exams, will we have to know this intuitively, or will we be given like a chart that has like common conversions, so we can just plug those in?
So conversions like density, you can't know, that will be given to you. Conversions between pounds and kilograms, given to you. Conversions between centimeters and inches, given to you. But conversions between prefixed and based units, you have to know. Good question. So if we had set this up at first as 1 cubic meter is 100 cubic centimeters, we would have been off by a factor of 10,000. It is 1 cubic centimeter to 1 cubic meter to 1 million cubic centimeters. That's a big difference, right? Okay, there's a few ways that we can do this. We could rewrite our numbers in scientific notation, or you can just plug it into your calculator. If rewriting them in scientific notation, 0.00157 becomes 1.57 times 10 to the negative 3. I move my decimal place over 3 times. And 100 times 100 times 100 becomes 1 times 10 to the 6. My units cancel exactly as I want them to. 1.57 times 1 is 1.57. 10 to the negative third times 10 to the 6 is actually just negative 3 plus 6. What's that? Negative 3 plus 6? Plus 3. Good. And my new unit, cubic centimeters. Am I done with my conversion? No, because I wanted mass, and I don't have units of mass. I still have units of volume. So now I do another conversion. 1.57 times 10 to the third cubic centimeters. I need to get out of cubic centimeters, I put it in the bottom. I need to get in to mass, I put grams on top. 0.9187. Does it go on top or on bottom? Which unit does it belong to? 0.9187 grams. Good. So it goes on top because it follows grams. And what number goes on bottom? Per centimeter. 1. per centimeter means per 1 centimeter. You guys seeing it? The hardest part here was converting between cubic meters and cubic centimeters. Okay, now this is just a calculator exercise, but how many significant figures should I be left with? I should be left with 3 sig figs. My density has 4, but my volume only ever had 3. Tell me if you get the same thing. $144,235.9 grams. You get something different? You did? Oh, you did plug it in. You got something different? Tell me what you get.
I got 1442.359.
Oh, that's because I did this conversion wrong. I put 3 zeros after 7, which is not correct. How many zeros after the 7? Just 1. Always good to double check your work. So I was off by a factor of 100. 1,442.359 grams. Can I be that certain down to the milligram of how much my ice cube weighs? No. How certain can I be? What's my final answer? Raise of hand. Jordan? Okay. The third significant figure. 1, 2, 3. So what is my final answer? 1,440 grams. Jordan, isn't that 4 sig figs? I have a trailing 0. There's no decimal point in the number. It's a trailing 0 in a number without a decimal point.
Why is the 0 there?
Because I can put it there.
Okay.
I had to round my 4. That's my last significant figure. That's my uncertain figure. And the number that rounds 4 is 2.
Yeah. Oh, so you tried it down. Okay.
So 2 rounds 4 to 4, but now 2 isn't there.
Okay.
Right. I round down to the 4. Now, if that confuses you, Blake, what's another way that you could write this number so that that 0 isn't there to confuse you?
Like 1.44 times 10 to the third.
Good. Take your decimal point, which is invisible there, move it to the left 3 times, 1.44 times 10 to the third grams. What's another way that you could report that answer without needing significant figures? Without needing scientific notation, by changing the unit. 1.44 kilograms. That's a big number and a small unit. So I can convert to a bigger unit and make that number smaller. 1.44 kilograms. Good. And now that 0 is not there to trip you up, right?
Yeah.
Okay. Questions? Saint?
I have a question about Baker's rounding. I'm not sure if it's applicable, but in the real chem, there was a problem where we're converting 55 meter squares to feet squared. And I got 59.2 and then the zeros continued, but it said that the correct answer was 590 feet squared. But there's
You got 59.2, but it said the answer was 590. So you're off by a factor of 10, which usually just means some sort of calculator error.
Okay, so it wasn't like Baker's,
But it also sounds like you kept an extra sig fig. You said 59.2, but they rounded 9. They took the 2 and rounded 9 down to 9.
oh, because we start with 55.
Okay,
Now
so
there's
2 sig figs.
Okay, that makes sense.
Great.
Thank you.
55 leaves 2 sig figs. All right. Any lingering questions on this?
I have another question.
Yeah.
Can you determine if there's two sig figs in 55? I think I remember reading something about how, like, if you have a whole number, you know what I'm talking about?
I do. Doesn't this feel like a whole number? 1,440? Well, I mean, I guess we rounded to that. But how are you to know that you counted 55 feet and that you didn't measure 59 feet? Typically, if it has that unit of something that requires a measuring instrument, you measured it. So if I'm doing a conversion between number of students and grade, then number of students is a whole number. I don't have to measure that, right? But if I'm saying the average height of something is 55 feet, that's something I have to measure. I can't count that. Does that make sense? If I don't have a measuring instrument that gives me below feet, doesn't give me inches, then I can only approximate to the feet. It's going to look like a whole number. It's going to look like I have 55, but I'm measured to that. What's the uncertain digit there? 5. Was it a little bit lower, 49.8, and I had to round up to 54.8, and I had to round up to 55? Or was it a little bit bigger, 55.1, but I had to round down to 55? So I rounded to a whole number. You were given a unit like that. That's a measured unit. Inherently just has 2 sig figs. It's a good question. So I think feel out the unit and ask yourself, did I need a device to measure this, or can I just point my finger and count it? You bet. All right, let's look at Module 3. We're kicking off Unit 2. Alina? Why did we lose it? Because I forgot. That's a great point. All of this should have been 1.26 times 10 to the negative 9, and this should have been 1.3 times 10 to the negative 9. Good point. I think you guys were on track with me that we were paying attention to the sig figs changing, and I just lost the scientific notation. Good point, Alina. Thank you. We could change it, right? And we could say 126 nanometers per second. Change the unit from meters, get to nanometers, and get rid of that scientific notation. But we didn't do that, so that was my fault. Thank you. You're welcome. Module 3. This is the part where it should start to feel like actual chemistry. Some of our learning objectives for this. We want to be able to interpret symbols for atoms and ions. We want to use percent abundance for average mass. I'm abbreviating average as AVG, but I think you guys would agree my V's look a little bit like U's. We want to be able to understand the evolution of the atomic theory. And we want to be able to interpret and recognize aspects of the periodic table. Any of you not get your periodic table this morning? Anybody else? Okay, I'll be honest, some of the evolution of the atomic theory is a little dry. It's kind of boring. So I think we'll breeze over it a little bit, and I'll point out the parts that help us understand the basic components of the atom. First of all, the Greeks were the first to propose the term atom. I think it meant indivisible. And they thought that there were atoms of water, atoms of dirt, atoms of air. And they were not far off, but as we know now, water has two different elements that make it up, 3 atoms total. Air sometimes is 1 atom, sometimes it is 2 atoms, depending on what substance you're looking at. Dalton was the first one to say that matter is made up of these small particles. And he said that atoms have characteristic mass. This led him to introduce elements. Atoms that have different masses are typically parts of different elements. And then he said that atoms cannot be created or destroyed. And this got us to the law of conservation of mass. The number of atoms you're working with is the number of atoms you need to end with. Now, some of you might actually look at what I just said. Atoms have characteristic mass, and then say equals elements. And you might say, that's not true. Because there are atoms made up of the same element that actually have different mass. So maybe we can modify this and say, this is approximately equal to the element type. But in the early days of chemistry, they didn't quite understand this. They were looking at these unique characteristics, and for the most part, the atoms they were looking at all had relatively the same mass. All right, so 2 things that these old scientists got out of doing experimentation with different chemicals. They got something called the law of definite proportions. Or the law of constant composition, which is to say, if you grab a substance, it's always going to have the same ratio of elements inside of it. So let's say that you go to the gas station and you take octane, that main component of the fuel. Every time you analyze octane, you're always going to get a 5.33 to 1 ratio of carbon to hydrogen atoms by mass. See?
Is this also called the law of multiple proportions?
It's not.
Oh, it's not?
It's very different, and they feel very confusing. Every time you get octane, it has this ratio. But does that mean that every time you find carbon and hydrogen together, you have this ratio? No. That was the law of multiple proportions. And I don't actually know the number offhand, so I'm going to try to calculate it in front of you guys. What's another common hydrocarbon fuel that you guys have worked with before, used in your lives? Think about grilling. What do you use? Propane. Or natural gas to heat your homes. Natural gas will be actually a little bit easier for me to work with. So let's go with this. If we're working with natural gas, this is methane. Methane has a mass of 3 to 1 for its ratio of carbon to hydrogen. So the same two atoms, but they appear in different ratios. That is the law of multiple proportions. It's to say that different elements, or the same elements, can come together in different ratios, but that changes only based on what that chemical is. And these guys, they didn't know as much as we do. They were leading the way. A lot of you are already familiar with different substances, what they're made of. It might surprise you to find out that they had to name these certain things. Every time I have a substance, it will have a definite proportion. It will have a constant composition. And if I have the same two elements that show up in different proportions, that just shows that the same elements can come together in multiple ways to make different substances. And then we can actually take a ratio of these. So let's say that we took this ratio of 5.331, or 5.33 to 1, divided by the ratio of 3 to 1, and we can say that the ratio between methane and octane, this multiple proportions, it's an ugly number, but it's 1.78 to 1, and that's their multiple ratios. Now you could take propane, butane, any of these hydrocarbon gases, and you could relate them. See?
I'm just a little bit confused as to where we got 5.331. Isn't the mass of carbon 12
Yeah. But if you weigh octane, if you look at a molecule of octane, each atom of carbon is 12, and there are 8. Each atom of hydrogen is 1, and there are 18. So you're actually taking 8 times 12 divided by 18. And that gives you a ratio of 5.33 to 1. So it's a little bit more involved beyond the scope of what we need to do right now.
Okay, thank you.
Your textbook gives a better example for the law of multiple proportions, one with copper and chloride, that has a nice even ratio. But it works for anything. You can say if I have this ratio between my compounds, that's the law. I don't really know what they got out of that law, but that is what they got out of it. So at this point, they know there are atoms. They know these atoms are made of unique elements. That these atoms have these specific weights. But they don't know everything else about this. What else these atoms are made up of. So then this guy, J.J. Thomson, comes in. He does an experiment with a cathode ray. Just means it's charged. So he's introducing charge into these analysis. And he finds that his negative cathode ray it gets deflected in different ways. So for one, his ray gets deflected away from negatively charged particles, and it gets deflected towards positively charged particles. So Thomson introduced this idea, there must be charged aspects inside of our atoms. Robert Millikan came in and actually gave more information about those charged particles. Using charged oil droplets, he figured out that the electron, I'm going to abbreviate this as E minus, it has a charge of a specific value, 1.6 times 10 to the negative 19th coulombs. based on the size of his oil droplets and how they were being deflected, he was able to put together all of this information. And he said the electron must have a mass that is 9.107 times 10 to the negative 31 kilograms. It's a big unit, first of all, and an incredibly small number. But even the numbers that we learned, down to femto and pico, it would still be an incredibly small number on the scale of picograms and femtograms. So electrons have basically no mass. So we know that atoms have specific masses, that they're made up, they're unique to these elements. We know that they've got charged particles, and we know something about one of those charged particles, the electrons. I actually forget, I made a typo up here. I called him Thompson. It's actually just Thomson. He comes back in and introduces the plum pudding model. He suggests that these electrons are floating around in a soup of positive charge. So you've got this atom that is just a big blob of positive charge, electrons floating around. That's what he proposes. And so what do his peers do to try and prove him right or wrong? They take a thin piece of gold foil and they start shooting alpha particles at it. So Rutherford says, let me shoot alpha particles, which they knew to be positively charged, but we today recognize as the helium nucleus. You'll notice I put some numbers in specific spots. Bottom left, 2, top left, 4, top right, 2+. By the end of today's lecture, I hope you can interpret what those 4 pieces, or what those 3 pieces of information mean. So Rutherford starts shooting these particles at thin foil. And if it were me, I might expect something to happen, which is they just bounce off the foil and they go backwards. But he finds that these particles sometimes go straight through, sometimes scatter to the sides, sometimes bounce straight back. So what is it that these alpha particles are running into sometimes and flying past other times and being deflected by other times? If your substance was made up of this big positive soup with little negative charges all around, you would expect complete repulsion. You wouldn't expect it to fly through it, and you wouldn't expect it to be deflected sometimes. So Rutherford proposes the nucleus. Atoms are mostly empty space with a positively charged nucleus. And you guys know the name of what gives rise to those positive charges? Protons. I don't use this as often, but you can abbreviate protons with P+ to signify what it is. But if you actually do the math, it turns out that the mass of the protons and the electrons does not come back to that characteristic mass of these atoms. So there's one last scientist, his name was Chadwick. And Chadwick proposes the neutron, which has no mass, which has no charge, and about equal mass to the proton. So I'm putting an abbreviation there, approximately equal to the mass of the proton. We're going to come back to talking about the theory of the atom and understanding how the electrons fling around this tiny, tiny nucleus. But what I want to tell you guys is that an atom's size, if it were the size of a tennis ball or an orange, if the nucleus, where all the protons and neutrons sit, if the nucleus was the size of a tennis ball or an orange, the atom would be about 8 kilometers across, the size of LA County. That's how big the atom is. Its nucleus makes up an insignificant amount of it. So the plum pudding model, how close was it? So far off. It's actually more like a big electron soup with this tiny little ball of positive and neutral particles sitting at its core. And that's why these alpha particles were able to shoot through it and sometimes would get deflected and sometimes would get shot straight back because they were flying through mostly empty space. All right, so here's what we get. The atom made up of its nucleus and then what we call the electron cloud. Basically, no size to the nucleus, all of the mass of the atom. The electron cloud is all of the size. Basically, none of the mass. So now we need a way to describe these elements and inform about all these different pieces of information, the charge, the protons, the neutrons. So we get this. We put a symbol in the middle. We put A, Z, and I'm going to put charge on the top right. A is the atomic mass. That's the sum of the number of protons and the number of neutrons in the element. Z is the atomic number. That's the number of protons in the atom. It is Z that defines the symbol. The number of protons alone is what tells you the element that you're dealing with. And what is charge? Well, charge is actually just the difference between protons and electrons. If you have more protons than electrons in an atom, you have an excess positive charge. If you have more electrons than protons in an atom, you have an excess negative charge. If you have an equal amount of protons and electrons, you have no net charge. So earlier I mentioned that this idea of characteristic mass is the element. It's not quite right. We introduce isotopes. Isotopes are atoms of the same element that have a different mass. What do they have in common, isotopes? Number of protons. What do they differ by? Number of neutrons. So I want you guys to do something. Take these two chemical symbols. C12 and C14. Use the periodic tables in front of you to figure out what element that is, or where it is on the periodic table. You'll actually notice the name's not on there. Find the atomic number. Fill that in. What is the atomic number for both of these chemical symbols? 6. You'll notice that your periodic table does not necessarily organize it like this, correct? You don't have a symbol with a number on the top left and the bottom left. On top of those symbols, at the top of each box, is the atomic number. And it's actually just sequential, top to bottom, left to right. So down here, if I wanted to fill this in, because I have chemical symbol C, I have atomic number 6. In the isotope of carbon-12, how many neutrons are present? You want to do that math for me? Good. Atomic mass is protons and neutrons minus the number of protons. 12 minus 6. Now somebody else. 8. 14 minus 6. 8. And we're not going to get into it this semester, but nuclear chemistry, things that involve changes in the nucleus of an atom, we can actually take isotope 14 of carbon, and we can flip one of those neutrons into a proton. Keeps the exact same mass. So tell me, if I get the same mass 14, but one additional proton, a neutron becomes a proton. What element do I get? And the chemical symbol? N. I think I might have introduced that on the first day in terms of the weak nuclear force. That's where that fundamental force is held. Unfortunately, these atoms don't always come out with exact even numbers like this. We say that the mass of a proton is approximately 1 AMU, and the mass of a neutron is approximately 1 AMU. But it's not exactly 1 AMU. In those situations where you need the exact numbers, they'll give you the exact numbers. But for now, I want to do a couple of examples with you on using some exact numbers. You know what? I think I'll let you guys have a break quick. I've pounded you hard enough. Let's go for about 5 minutes. Get up and move around, even if you're not going to leave the room, so you get your blood flowing a little bit. Kristen. Welcome. Yeah.
So for the baker's rounding,
Mm-hmm.
if it was a 5, we round to the nearest even number. Why did we round it 2 and not like 0 or something? Because they're both even numbers, right?
In Banker's rounding, if the number after the last significant figure is 5 and only 5,
Yeah.
then you round to the even number.
Okay. Yeah.
What
So
example did we round?
It was 12.15.
Right.
Yeah. So 2 is an even number.
Oh,
But also 0.
and I rounded to 12.2, didn't I?
Yeah. So.
Oh, sorry. So you're saying if we had 12.15, this is my uncertain digit.
That
Is
we're
it-
rounding.
Is it 1 and a little, right, because I said, well,
Yeah.
let's say we have 3 sig figs. Is it 1 and a little more, or is it 1?
I mean, 1 and a little more. So.
It is 1 and a little more. So it's going to become 12.2.
Okay.
But here, 12.25, my uncertain significant figure, is it 2 and a little more, or is it 2? We're going to say it becomes 2.
Because it's already even.
Yes.
Okay.
So your question was, why don't I take 12.15 and round it to 12.0? Either we round 1/5 down to 1, or we round 1/5 up to 2.
So it doesn't. It never like goes.
But I never actually change. I either keep 1 or I go up.
Okay. All right. That makes more sense. So you never go down.
That's right.
Okay.
You'll never take this uncertain digit and make it a smaller number.
Okay.
You'll either take the whole number and make it smaller by limiting it to this, or make it larger by rounding it up to this.
All right. I get it.
It's a good question.
All right. Thank you.
You're welcome. All right. Oh, we're still empty in here. I added a little bit more information on the board. I wrote up the exact numbers and not just those approximate numbers so that we can do some math with them. But I want to point out something. AMU is a unit. It's an abbreviation. Do you guys know what it stands for? Exactly. It's a made-up unit. Well, all units are made up, but this was a made-up unit for the sake of atoms. Oh, by the way, somebody was asking me about Banker's rounding. How come the 1 doesn't go to 0? Why does it go to 2? 0 and 2 are even. And I just wanted to point out, this whole number either gets rounded down to 1 or it gets rounded up to 2. That's all I was pointing out. You'll never actually change that 1 to a smaller number. Okay, so atomic mass units, a unit created to represent the mass of these atomic, subatomic particles in an easier way. You can see that a neutron weighs slightly more than a proton, but enough to make a difference in when you have a large number. Do you notice anything strange about the mass of the proton and the mass of the neutron? No? Coming out of our conversation about significant figures? The neutron has one more significant figure. So I want you to think about when these got reported, some scientist was more limited in measuring the mass of the proton than they were in measuring the mass of the neutron. Food for thought. I'm not going to tell you how because I don't know. And the electron has an approximate mass of 0 AMU, but you can see that its actual mass is about 0.5 milli AMUs. So it's half of a thousandth of an atomic mass unit. So when you add all of them up, it's insignificant compared to the mass of the protons and the neutrons. Okay. Carbon-12 and carbon-14 do not have equal abundance on Earth. That's why carbon-14 is useful in carbon dating. We can tell how old a sample is by how much carbon-14 is in it, or how much radiation it gives off as it converts to nitrogen-14. And so we can actually do some atomic abundance calculations, and that's where we're headed here. Under isotopes, we're talking about, isotopic abundance. This is what leads us to an average atomic mass. I'm actually going to go away from the example of carbon-14 and carbon-12 because carbon-14 makes up such a small amount of carbon isotopes, it hardly registers on the average atomic mass that you see on your periodic table. And instead, I want to go to a couple of other examples. The first one is bromine and its 2 primary isotopes. So this average atomic mass can be calculated using an equation that big Greek letter sigma in the front. Anybody know their math? Yeah, this is the sum of all of the isotopes, mass times their fraction of abundance. So if you can say that all of the isotopes of a specific element add up to 1, then each isotope makes up some fraction of that whole 1. So bromine has 2 isotopes, excuse me. One of them makes up 51% of all bromine. So I'm writing that fraction as 0.51. The other makes up 49% of all bromine, 0.49. Now we need to do a little bit of reconnaissance because my notes are not actually completely accurate here. Can you tell me how many protons are in bromine? How do you know that there are 35 proteins in bromine? So for those of you learning your periodic table, bromine is closer to the right. It's in this second to last column, and it's the third one down, Br. That number on top is the atomic number, 35. That's how many protons it has. What is the mass of all of those protons? Well, about 1 AMU, so 35, or 1.007 AMU. I think I heard somebody trying to say 79.9. That's the average atomic mass on the periodic table, but that's not the mass of the protons. All right, the neutrons differ in these 2 examples. The first bromine isotope is called bromine 79. So we can put that up here, bromine 79. How many neutrons in bromine 79? 79 minus 35. So if you don't know that number off the top of your head, just do what Ryan did. Grab your calculator quick, prove it. Times its atomic or its mass, 1.0087 AMU. So now I want to get the actual mass here of bromine 79, and I want to multiply it by its fraction, 0.51. So I'm going to plug in my calculator, and I'm going to use parentheses to make sure I do this right. So first, parentheses, 35 times 1.007. End parentheses, plus parentheses 44 times 1.0087, end parentheses. What I'm doing is making sure that my numbers here get multiplied correctly and that my order of operations doesn't get screwed up anywhere. That gives me an actual mass of 79.6278 atomic mass units. Should I keep all of those digits? I've got 4 sig figs from proton, 5 sig figs from neutron. These are whole numbers, 35 and 44. And this is more than 4 sig figs. But I'm not done with all of my calculations yet, so I'm going to wait to round. I'm going to notice that this is where I will round 4 sig figs, but I'm not going to round yet. Can you do that to give me the actual mass, well, I have to tell you, of bromine 81? Calculate how many neutrons are in bromine 81, and then give me the actual atomic mass of bromine 81. If you have your calculator, practice with it. Make sure you know how to use it, because you will be doing this on the unit test, And you'll be doing this on the midterm. Get to know your calculator now. Who's got a number for me in terms of number of neutrons? Shouldn't be hard, right? 79 to 81. That's an increase in 2 mass units. No change in protons. That's 44 to 46 neutrons. What is the atomic mass of bromine 81? 81.6452. All right. Units AMU. Good. And again, we know that we're going to round this number at some point to 4 sig figs. So I'm just reminding myself, I really only have 4 sig figs, but I'm going to do all the rounding at the end. Saint. Do I need to limit myself to 2 sig figs because of 51% and 49%? Do I need to limit myself to 2 sig figs because of these percentages? Do I need to limit myself to 2 sig figs because of the number of protons and neutrons? These are counted numbers, so we're going to say they do not limit our sig figs. Does that feel like a good application for you about your question earlier? Great. All right, more calculator exercise. Here's what I'm going to do. In parentheses, 0.51 times. Now, if you have this function, you can actually scroll up to get that number you calculated earlier. So I'm going to scroll up to 79.6278 and grab it. It brings it down, end parentheses, plus 0.49 times, scroll up to 81. Oh, I never calculated 81. You guys got me there. I'm going to have to just plug it in. 0.49 times 81.6452 equals what do you get? What? Did you divide by 2? You took an average by dividing by 2. But we actually already calculated the average because it's not a perfect 50-50 mix. So only 51% weighs 79, only 49% weighs 81. That's what I'm getting on my calculator as well.
You just took that whole thing and just entered it into your calculator.
That's right.
Okay.
So I'm going to write it down. For bromine, 80.616326 AMU. Final answer? Good. Mark, what do I round it to? Let's identify how many sig figs. How many? Four here. 4 here. So what digit is my last significant figure, Jackson? The 1. Good. Hayden, does that 1 stay 1 or does it round up to 2? It rounds up to 2. Why? Good. 6 is bigger than 5. So my final answer here is 80.62 AMU. All right, I want you guys to check your periodic table. Does it agree?
Well,
Kind of almost. If you do this calculation using 79 and 81 in these places instead of a number larger than 79 and a number larger than 81, you actually get what your periodic table says, which is 79.9. But if you do it using these, you get something else. So that might be telling us something. There are more isotopes of bromine that actually influence the total average atomic mass. and that this example was not set up well to compare with your notes or with your periodic table.
When we're performing these calculations for, I don't know what you call it, like isotope
Yep.
abundance,
Yeah.
do we always assume that the significant number that we're going to round our final answer to is 4 because protons, neutrons, and electrons all have 4 significant numbers for the A and U? Like up there.
Yeah, that is a good answer. Yep. You're probably going to round these all to 4. All right, now I want you to also be able to run this backwards so that given key pieces of information, you can actually get to the mass of a missing isotope. So now we're going to work with chlorine. Chlorine has 2 main isotopes. And their average atomic mass is 35.453 AMU. Actually, I'll tell you what they are. These are chlorine 35 and chlorine 37. That's just what we call them. It's not their exact masses. These are their exact masses. There's some isotopic fraction, X, an unknown, for chlorine 35. And we're going to say that the exact mass is 34.96. And this makes me really skeptical of the source I got those masses from earlier. So I'm going to do some checking on that. If I have 2 isotopes, and one of them has a fraction X, how much does the other isotope make up? Not X minus 1, because X is a part of 1. 1 minus X. Good. 1 minus X for chlorine 37 with a mass of 36.96. I have 2 unknowns. The amount of chlorine 35 and the amount of chlorine 37. But they're actually written as one unknown. However much chlorine 35 is, and then that subtracted from 1. I don't know how much chlorine 37 is, but I know it's whatever is left over in 1 from whatever chlorine 35 was. Yeah? So just one unknown here. So we can do a little bit of algebra. This number, 35.453 AMU, gives me 34.96 X plus 36.96 minus 36.96 X. Oh, didn't you miss foiling things? Or factoring? No, it's foiling, right? Distributing. Sorry, I'm not a math professor. This mass gets multiplied to 1, and it gets multiplied to X. So I get 36.96 minus 36.96 X. And now I can rewrite this as 36.96, which has a unit now of AMU. And now I can take 34.96, and I can actually subtract 36.96. 34.96x, 36.96x. In subtraction, how do I manage my sig figs? Least number of decimal places, which is 2 and 2. So I actually get minus 2.00 x AMU. What is x again? It's the fraction of isotopes that chlorine-35 makes up. I don't know how much chlorine-37 is. It's just whatever is left over from 1. Do you notice how I have a negative number? That's because I'm not done yet. I need to solve for x. So I'm going to subtract 36.96 AMU on both sides. So I get 35.453 minus 36.96. That's negative 1.4507 AMU is equal to negative 2.00x AMU. I want to solve for x, correct? I don't have x. I have negative 2.00x. X equals negative 1.507 divided by negative 2. Do you see that? That gives me 0.7535. Can I write that as a percentage? How would you write that? Per 100. So I need to multiply by 100. 75.35% of chlorine is chlorine-35. 3 out of every 4 atoms of chlorine is the isotope chlorine-35. So roughly what percentage is chlorine-37? Yeah, just less than 25%. How would I find the percentage of chlorine-37? 1 minus x. Whatever is left over. Yes?
I'm
Tell
sorry, I'm confused.
me.
This is the questions where we're finding out the percentages.
Here I gave you 51% and 49%.
Yes.
But here, we need to figure it out based on already knowing the average atomic mass.
Got it.
Yeah?
Thank you.
You bet. Saint. And then Alina.
Wait, how did you get 24.65%?
I did 100 minus 75.35. What's left after 75%? It's 100 minus 75.
Why did you do 100?
Because that's the total. I actually didn't do 100. I did this, Saint.
I can't see that.
It says 1 minus x.
Okay.
And what is x? 0.7535. And that's a fraction out of the total 1. All atoms of chlorine are a set, 1. There's one set of chlorine atoms. 0.7535 is chlorine-35, 35%. The rest, 1 minus x, is chlorine-37.
So that top one, the 75.35, goes to that one, the x times or plus.
We said x times chlorine-35, which is actually 34.96. And we said whatever is left, 1 minus x, is chlorine-37, 36.96.
Okay, that makes sense. Thank you.
You bet. Alina.
Didn't you go finalize also like 75.35? the sig figs? Because as I understood in our confusion rule, they had the least number of sig figs like 3.
Okay, so this is a good application of sig figs and calculations. And I want to make sure I'm saying it right. Whatever function you do first in a calculation, sometimes your calculations include PEMDAS, parentheses, exponents, multiplication, division, subtraction, and addition. Whatever function you do first will be how you decide to limit significant figures at the end. If you do subtraction inside of a parentheses as your first thing, and then you go on to do multiplication and division, you will limit based on that first function. Limit by the least number of decimal places in that subtraction. If you do a big calculation like this, and you start with multiplication and then go on to do subtraction or addition, you're going to limit based on that first function, multiplication, which is the least number of sig figs. And here, I had 4 sig figs or 5. So I'm going to stay with 4 sig figs or 5 because I started by doing multiplication. And then I did some subtraction, and I did some addition actually. No, I guess that's also subtraction. And then I ended with, but my first function was multiplication. So I'm going to stick with least number of sig figs rather than ending with subtraction. Or no, that's also a division, but still. Did that answer your question? Your calculations can be as complex as they need to be. Limit it to that first function. You bet. All right, I am not happy with the numbers that I had before, so I'm going to try and find the better numbers. I have a feeling that these numbers we did with bromine were not supposed to be larger than 79 and were not supposed to be larger than 81, but they were actually supposed to be smaller than those, which is why our number was supposed to be smaller than the one we got. I trusted the AI overview on Google to give me those masses, so maybe something is wrong with those masses. I'm going to check on that and get back to you guys on it. But in the meantime, do you have questions on these calculations? Sing.
For our exams, would we be expected to know like these masses, these AMU masses, or would they be provided?
Those would be provided if you need them. You would not be expected to know them, especially since I'm hesitant to believe them. Yeah, you bet. Okay. How do you think they find out these percentages? How do they know that there's 51% bromine 79, 49% bromine 81? We use an instrument called a mass spec or mass spectrometry, which is literally measuring the spectrum of mass. And mass spectrometry is cool. It involves magnets pulling charged particles, but depending on the weight of that charged particle, they get pulled by the magnet to different extents. Kind of like pulling on a block that's 10 kilograms versus pulling on a block that's 100 kilograms. They're going to get pulled to different extents, which means that they get pulled by the magnet a little bit differently, and then they hit a detector in a different spot, and that detector says, if I get hit here, it means the magnet pulled this strongly, which means that charged particle has this mass. But if I get hit over here, it means the magnet pulled more strongly, so that charged particle has a smaller mass. But they have to be charged particles. And this introduces us to ions. Atoms are charged ions, so there is a discrepancy between the number of protons and the number of electrons. We have cations and anions. I think the best way to remember this is just with some fun. Cations are positive, like a cat. Anions are the antagonist, negative. Which ion has less electrons than protons? Cations have less electrons. Which ion has less protons than electrons? Good job. Cations, protons greater than electrons. Anions, protons less than electrons, or number of, yeah? And I showed you earlier that we can actually put that charge up in the top right corner. So here's a couple of examples of ions. Oops, I put that in the wrong spot. My chemical symbol, Mg, with charge 2+. But I can add more information in. I could call this Mg, which has 12 protons, 24 mass, and a charge of 2+. I can start to fill in that atomic symbol a little bit more. Cation. Or I can have O, 2-. Or I can fill this in more. And I can say O16, atomic number 8. Berkeley, how many protons in this magnesium atom? Good. And Carly, how many electrons in this magnesium ion? Good. 12 protons with a positive 2 charge. 2 equals 12 minus the number of electrons. Then I just have to do some weird algebra, and I get 10 electrons. Good. Who else can I call on? Jacob? How many protons in this O2- ion? And Danila, how many electrons in this O2- ion? The charge is related to protons and electrons, not to the neutrons. There are 8 protons. How many electrons in this O2- ion? Are there at least 8 electrons? That would balance out the 8+. Are there more than 8 electrons? How do I then have an excess of 2-? Right? I need to have at least enough electrons to balance out the protons. Then I need, Caden? 10. I need 2 more electrons than my protons. 10 electrons. I gave you guys that equation, charge equals P minus E. That's algebra. You can plug everything in there and it will work out. So here, 2- equals 8 minus electrons. Well, I'm going to end up subtracting 8 on both sides. Oh, I think I said plus electrons, right? No, I said the difference. Well, listen, I don't know. I'm not a math professor. You have to figure out, I'm going to erase it because I don't want it to confuse you more. There is algebra you can do, but honestly, you can feel that out too. Balance the charge, then work out which way you need it to be offset.
Alice, like, how do you know how many electrons there are, and where did you get the plus 2 and then the minus 2?
I gave that to you. I gave you an example. This is a magnesium ion, Mg2+.
Will we be asked to find like the plus 2 or the minus 2?
If you're given the number of electrons and protons, yeah.
What is the plus 2 and the minus 2?
Charge. That's the charge on the atom.
And we find the charge by P, so protons minus electrons.
Yeah. Although I think my math just showed it might have to be protons plus electrons. Right, because they have opposite charges. It's terrible. Oh, you can't have negative 10 electrons. That's why that number's looked right. I'm going to put it back up. If I have a minus 2 charge and I have 8 electrons, or 8 protons, I subtract 8. A negative 10 charge equals negative electrons. How can I have a negative 10? I'm trying to find the number of electrons, not necessarily a charge, just a number of electrons. How many electrons do I have? 10. Okay, I scared myself doing the algebra, but I was on the right track. How could you know this, Saint? You can't. I gave it to you.
Okay.
But let's work it in reverse now. I have an atom that has 11 protons. And it has a charge of +1. It has 11 neutrons as well. I want you to find the number of electrons, and I want you to write its chemical symbol. Do you want to put it on the board? Don't let Ryan steal this opportunity. Do it. Still work on it. Use your periodic table. Write that chemical symbol. Not where I would have put it, but that's okay. Just to the right of it.
You want me to like write everything?
Yeah, yeah. Do you want to solve for E?
Oh, yeah, good.
You just
I
write
don't know
it.
how to. Okay.
Good. Work, Ryan.
Thank you. I perform better under pressure.
How did he know it was Na?
Number of protons.
He looked at the number of protons and followed the periodic table down to where it said 11. He found atomic number 11, which is Na, sodium. And then he put that atomic number on the bottom left. That's where Z goes. How did he know to put 22 on top? He summed 11 and 11. Is this the main isotope of sodium? Look at the average atomic mass of sodium, 22.99. What do you think the main isotope of sodium is? 23. Because it's basically 23. It's just a little bit offset below. And how did he know that the number of electrons was 10? Saint? How did he know the number of electrons was 10?
Great question. I have no idea.
So I told him the charge, and he knew the number of protons. if there's an excess of positive charge, that's an excess of protons, which means he must have fewer electrons. By how many? Just fewer by 1.
Wait, so the charge equation that you gave us that says charge equals P minus E, that's how we find
You can find it that way, yeah. You can find P or E that way, or charge.
but we're not given electrons on this, so how do we find like
You plug it in like this. Leave E as an unknown and solve for E. Good. Now there is something we didn't get to today, which is looking at groups on this periodic table. Classifications, families. So I want to pick up with that on Wednesday and have you guys bring these back, or if you're not going to bring them back, give them to me so I can give them back to you on Wednesday. But bring these back on Wednesday so that we can make some observations on these. You cannot bring this to the test, like the midterm and the final. They will give you one that's blank. But I want you guys to have one for your own to work on, to get familiar with, so that when you go to the midterm, you know how to use it. This, blank. Yep.
wait, blank, like we have to fill it in just
No, just this. You can't have annotations on it.
Oh, okay.
Not empty. That'd be crazy. All right. Have a good day, guys. I will see you tomorrow.